Hello, welcome to the course PH5BO6 Electrodynamics 2. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. In today's class, we will continue to discuss topics from Chapter 7, Electrodynamics. In the last couple of lectures, we discussed about Maxwell's equation. In particular, three scenarios were discussed. First one, the most general case, that's for free charges and currents. Secondly, Maxwell's equation in the case of free space. And finally, what happens in the case of materials. In today's class, let's talk about electrodynamics boundary condition. Now, from the previous chapters, we have seen that in general, the electric and magnetic fields will be discontinuous at a boundary between two different media. So in today's class, let's see whether this is going to be the case when we have electrodynamic fields. So as always, we will assume that our boundary surface carries a charge density sigma and a current density K. So let's assume that the field is moving from one material medium to another material medium. So let's take the Maxwell's equations in matter. Divergence of D equal to rho F, divergence of B equal to 0, curl of E equal to minus dou B by dou T, curl of H equal to JF plus dou D by dou T. Now this is the differential form of Maxwell's equation, and if you write these equations in the integral form, the analysis is going to be easier. So let's convert all these differential equations into integral equations. We have done this in the previous chapters. Anyway, I will give you a quick recap. So take the first equation and do a volume integral. So volume integral of charge density gives you the corresponding charge enclosed within the volume. Similarly, if you take volume integral of divergence using Gauss theorem, you can write it as surface integral of the corresponding function. So left hand side becomes surface integral d dot dA equal to QF enclosed. Follow the same procedure, you get the second equation converted into surface integral B dot dA equal to 0. Now the third equation, apply a surface integral. Now on the left hand side you have surface integral of curl. From Stokes theorem you know that this is equal to a line integral of the corresponding function. So LHS becomes closed line integral E dot dl, and the right hand side becomes minus d by dt surface integral B dot dA. Now this is nothing but the flux, and integral E dot dl is the EMF. So EMF equal to negative rate of change of flux. This is the flux rule. Same way you can convert the fourth integral as well. Apply the surface integral. Left hand side becomes integral H dot dl. Now surface integral of the current density gives you the line current IF enclosed by the surface. And the second term gets modified as d by dt surface integral d dot dA. So as I said, we have a two-dimensional boundary surface containing a surface charge density sigma and a surface current density K. Now assume that you have a very thin pillbox intersecting this surface. This is the top side of the pillbox and this is the bottom side of the pillbox. Okay. So let A be the surface area of the top and bottom side. As I said, this is a very thin pillbox. So this thickness is almost 0. Now let's take the first equation and find out this surface integral. Now the top side let me call as 1, bottom side let me call as 2. So on the top hand side the corresponding field is D1, displacement field D1, and bottom side I have displacement field D2. Now D is uniform, so you can take it outside the integral. So this is D into surface integral dA Surface integral of dA gives you the corresponding surface area. So basically you need to find the product of displacement field D and the area A for all the 6 sides. You have top side, bottom side and 4 sides on. Okay, so let's do that. For the top side, the field is D1 and the area vector is A. Both are along the same directions. You can write it as D1 dot A. For the bottom side, field is D2, which is pointing upward, and the area vector, as you know, it is a normal vector, so it is pointing downwards. So these two are in the opposite direction. So you have a minus here, minus D2 dot A. Now you have to find similar dot product for all the 4 sides, but since the thickness is almost 0, the corresponding area is also 0. So this dot product gives rise to 0 contribution. Okay. So essentially you have 2 terms corresponding to only the top and bottom side. Now this is equal to QF enclosed, the total free charge enclosed by this surface. Now charge can be written as a product of charge density multiplied by corresponding area. Now I can consider 2 components for the field, one perpendicular component and one parallel component. Let me consider the perpendicular component first. As you can make out, the perpendicular component of displacement field and the area vector both are along the same direction. So dot product of 2 parallel vectors, this is nothing but a normal product of the corresponding magnitude. So you can write D1 perpendicular into A minus D2 perpendicular into A equal to sigma F into A. A is common, so I can cancel that and write D1 perpendicular minus D2 perpendicular equal to sigma F. The perpendicular component of the displacement field is discontinuous by an amount sigma F. You can do the analysis using the parallel component, but as you can easily make out, the parallel component of the displacement field and the area vector are perpendicular. The dot product of 2 perpendicular vectors always give you 0. So 0 minus 0. This is essentially a trivial solution which won't give you any insights about the material under study. So let's only consider those solutions which will give us more insights about the electrodynamics problem here. So in this case, it is the perpendicular component which is useful for my analysis. Now same way, take the second equation, do the same procedure, find out this surface integral for all the 6 sides. You can make out the 4 side contributes nothing, only the top and bottom side contributes, and if you take the perpendicular component you get B1 perpendicular minus B2 perpendicular equal to 0. So as always, the perpendicular component of magnetic field is continuous. Moving on to the third equation, integral E dot dl equal to minus d by dt B dot dA. So once again we have a 2-dimensional boundary surface carrying a current density Kf. Let's assume an Amperian loop of length L and negligible width. So this Amperian loop is intersecting the interface. This is the top side and this is the bottom side. Now we need to apply the line integral for this Amperian loop. Now the electric field is uniform, you can take it outside the integral. So this is E into integral of dl, which is nothing but E dot the corresponding length. So you need to find E dot L for all the 4 sides here. Now for the top side, the electric field and the length are along the same direction. So you can write it as E1 dot L. For the bottom side, the electric field is in this direction, but the length is in the opposite direction. So you have a minus sign here, minus E2 dot L. And for these 2 sides, Since the width is negligible, you can assume that this length is almost equal to 0. So these two sides do not contribute to the line integral. So this is equal to minus d by dt integral b dot dA. Since the width is negligible, the area of this loop is also negligible. So you can say the flux through this loop is 0. So the right hand side conveniently you can put as 0. So E1 dot L minus E2 dot L equal to 0. Now you can consider that the field consists of two components, one parallel component and one perpendicular component. So let's take the parallel component first. Since the parallel component of electric field and the length both are along the same direction, the dot product can be replaced by a normal product. So you get E1 parallel minus E2 parallel equal to 0. If you take the perpendicular component of electric field, this dot product always go to 0. So you get a trivial solution which is of not much use for us. So the parallel component of electric field is continuous across a boundary. The same thing you can do for the fourth equation. You can calculate this line integral for all the four sides, and you will find that only the top and bottom sides are contributing. So you can write h1 dot L minus h2 dot L equal to IF enclosed. The second term goes to 0 because the area enclosed by the loop is negligible. So this goes to 0. Now this equation is written in terms of the line current IF enclosed. On the other hand, the boundary surface is characterized by the surface current Kf. So we need to write the IF enclosed in terms of the known parameter Kf. So if you recollect the definition of surface current, this is nothing but line current divided by the corresponding length, or line current can be written as surface current multiplied by the corresponding length. Now you may be tempted to use L as the length segment here, but look at the configuration. Kf is in this direction and L is in the perpendicular direction. So if you just write IF enclosed equal to Kf dot L, dot product of two normal vectors gives you 0. So you get the current equal to 0. So this is not the line segment we have to consider. We have to consider a length along the direction of the current flow. Now how do we get that? Assume a unique normal vector n cap, and if you take n cap cross L, you need to apply the right hand thumb rule. Place your right hand along the direction of n cap and curl it towards L. So the direction of thumbs gives you the direction of cross product, and you will find that it is along this direction. So n cap cross L and Kf are along the same direction. So you can write IF enclosed equal to Kf dot n cap cross L. Now this is a triple product. In a triple product you can interchange the cross product and dot product. The value remains the same. So this is equal to Kf cross n cap dot L. So instead of IF enclosed you can write this here. So the dot product is common. So you can cancel that and write H1 parallel minus H2 parallel equal to Kf cross N. So the parallel component of the magnetic field or the auxiliary field is discontinuous. Now you can combine this result and write it for the case of linear media. If you recollect, for linear media, displacement field D equal to epsilon E, where epsilon is the permittivity of the material. Similarly, auxiliary field H equal to 1 over mu into B, where mu is permeability of the material. So the first result we can write as epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular equal to sigma F. Second result remains the same, B1 perpendicular minus B2 perpendicular equal to 0. third result remains the same, E1 parallel minus E2 parallel equal to 0. In the fourth equation, it becomes 1 over mu1 B1 parallel minus 1 over mu2 B2 parallel equal to Kf cross M. So these are the boundary conditions for the case of linear media. So let's consider a special case. Imagine a situation where you have 0 charge density and 0 current density. So this is true for the case of insulators or dielectrics. So these equations get modified as epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular equal to 0. Second and third equation remain unchanged, and the fourth equation becomes 1 over mu1 B1 parallel minus 1 over mu2 B2 parallel equal to 0. Now these four equations are very important in describing optical interaction. If you remember my previous class, I said one of the biggest applications of electromagnetism or electrodynamic theory is in the case of optics, because as you know, light is an electromagnetic radiation. Now if you go into your physics lab, you will find out that most of the optical components which we use to control light, like mirrors or prisms, lenses, wave plates, etc. These all are made of dielectric materials like glass, quartz and other crystals. Now when light passes through these kind of optical components, the optical interactions happening there you can describe in terms of these equations. I'll give you a simple example. Suppose light is passing through a glass plate, right? So here you can model this situation as an electromagnetic field traveling from an air medium into a glass medium. So you have two media. In between the media there is an interface. As we have seen, the electric and magnetic fields are discontinuous at the interface. So whatever processes happening at the interface you can analyze using this boundary condition. Now what happens at the interface? A part of the light can get reflected and the remaining part can get transmitted or scattered. So all these processes like reflection, refraction, transmission, etc. you can analyze using these electrodynamic boundary equations. Now we will use these equations extensively when we talk about electromagnetic waves in chapter 9. So that's about the boundary condition. And before winding up, let's do a simple problem. Seawater at frequency nu equal to 4 into 10 to the power 8 Hertz has permittivity epsilon equal to 81 epsilon naught, permeability mu equal to mu naught, and resistivity rho equal to 0.23 ohm meter. What is the ratio of conduction current to displacement current? So clue is given. Consider a parallel plate capacitor immersed in seawater which is driven by a voltage V0 equal to V0 into cos 2 pi nu t. So we need to calculate conduction current JC and displacement current JD and find out the ratio of these two. Now conduction current from ohms you can write this is sigma E, where sigma is the conductivity, which is nothing but 1 over the resistivity. Electric field is the gradient of potential, so you can write it as V divided by D, where D is the distance between the two plates of the capacitor. So JC equal to V over rho D, which is V0 cos 2 pi nu t over rho D. And the definition for displacement current, dou D by dou T, and the displacement field D equal to epsilon E. Epsilon is a constant, take it outside the derivative. This is epsilon into dou by dou T V over D. And if you take the derivative of cosine, you get a minus sign. So this is epsilon V0 over D into minus 2 pi nu sine 2 pi nu t. So you have expression for JC and JD. Take the ratio of these two And let's take only the ratio of the amplitude. You don't have to bother about the phase term. Basically, the phase term tells you that JC and JD are out of phase by pi by 2. Right? So this basically talks about the phase relation. So let's consider only the amplitude now. So take the ratio of the amplitude, plug in the values, you get around 2.41. Okay. So that's about the chapter electrodynamics. In the next class, we will talk about conservation principles applicable for electrodynamic fields. Thank you.